A 3-phase 11 kilovolt 50 Hz 200 kilowatt load has a power factor of 0.8 lag. A delta connected 3-phase capacitor is used to improve the power factor to unity. The capacitance per phase of the capacitor in microfarads is. So we will see how to do this problem. First we will write the case where the line is not yet compensated, right? So before compensation we have the active power, it is given as 200 kilowatt and the power factor is also given 0.8, that is lagging power factor. Okay, so 200 kilowatt and cos phi is 0.8. So if you construct the power triangle, this is P, this will be Q and this is the angle phi. So we know phi, we can find out phi. So from here you can find out the reactive power as well. The reactive power Q is equal to P tan phi. Okay, so this answer you are going to get 150 kilovolt ampere reactive. This is before compensation. Now after compensation, what is the goal here? It is given here. The delta connected capacitance is improving the power factor to unity. Okay, so if you take this, we will use the subscript 1 here, cos phi 1 q1 p1. Okay, so after compensation, cos phi 2 is equal to 1. So under unity power factor, phi 2 will be nothing but 0, right? So this is P and the initially we have Q1. This should be completely compensated by the capacitance. So we will take this to be QC. So what will this be? It will be equal to Q1. Now in the question they ask the capacitance per phase. So first we will find out the reactive power to be supplied by the capacitance per phase. So what will this be? This will be equal to Q1 divided by 3. For a 3-phase system, balanced system, it will just be divided, total reactive power divided by 3. Okay, so this we got as 150. So divided by 3 is going to give you 50 kilovolt ampere reactive. Now one more important thing that is given here is the load is delta connected. So for a delta connected load, what will be the relationship between the phase and the line voltage? See, irrespective of the transmission line configuration, what we have is the capacitance configuration that is delta connected. So say the transmission line is giving you the line voltage VL, then that becomes the phase voltage for the capacitance. Okay, so we don't have to consider what is the configuration of transmission line. We are only concerned about the configuration of the capacitance bank. Okay, so here V phase is equal to the V line and this voltage is given as 11 kilovolt. So the key here is to not write 11 by root 3. It will be equal instead. Okay, so now once we know the voltage across the capacitance and the reactive power, what will be the relation here? QC phase is going to be the phase voltage divided by the reactance. So this is going to be V phase square divided by 1 by omega C. This is per phase value. So from here C phase is going to be QC phase divided by V phase square into omega. So this we know anyways, 50 into 10 cube because it is in kilo, and V phase square is 11 kilovolt, so 10 to the power 6 into frequency is given as 50 Hertz, right? So 2 pi into 50. So this if you calculate, you are going to get 1.31 microfarad. So what is the option here? The option is B, 1.316. So it is given in microfarad, all of these options. The ABCD parameters of a 3-phase overhead transmission line are given. Okay. At no load condition, a shunt inductive reactor is connected at the receiving end of the line to limit the receiving end voltage to be equal to sending end voltage. The ohmic value of the reactor is. So we have already discuss this under no load the required shunt reactance so that Vs is equal to Vr. This is going to be B by 1 minus A. Okay. So what is B here? 200 angle 90 degrees divided by 1 minus 0.9 angle 0 degrees. Okay. So you are going to get 2000. You can write J 2000. So this will be the ohmic value of the reactor. A lossless transmission line having surge impedance loading of 2280 megawatt is provided with a uniformly distributed series capacitor compensation of 30%. Then the surge impedance loading, SIL is surge impedance loading of compensated transmission line will be. So the initial uncompensated surge impedance loading, this is given as 2280 megawatts. And what is the compensation? Here it is a series compensation and the percentage is given, right? So that we have taken as KSE. So this is 0.3. Now we want the surge impedance loading of compensated transmission line. Okay. So this surge impedance loading, it is going to depend inversely on the surge impedance, right? So we have to first find out then how is the surge impedance varying with the compensation. So we have discussed that Zs dash will be equal to Zs into root over 1 minus KSE for a series compensation. So if shunt or capacitance is given, then we have to include that terms as well. So whichever terms is given, only that we have to include. Okay. So in a similar manner, if you take for the compensated SIL dash, we will take to differentiate. Okay. So SIL dash divided by SIL will be what? It will be equal to 1 by Zs dash divided by 1 by Zs. Right. So this is going to be Zs by Zs dash. So from here you are going to get Zs by Zs dash is going to be equal to 1 by root over 1 minus KSE. So now what? SIL dash we don't know, SIL is known, KSE is known. So we just have to substitute, right? It's a matter of substitution now. SIL dash is going to be equal to SIL is 2280 divided by root over 1 minus 0.3. So this if you calculate, you will get 2725 megawatts.